Module 9, Non-Biological Buffer System. Hello and welcome everyone. Thanks for tuning in with me today. I'm Jordan Larenfeld and today I'm going to be talking about buffers. In particular, we are going to talk about non-biological buffer systems. Let's get started. Okay, let's start by reviewing buffers. What are buffers? Well, it is a solution that can resist change to pH at a specific pH range. Some buffers resist change as well at a pH of 2 to 3, and others resist change as well at a pH of 7 to 8. A buffer solution contains an appreciable amount of both of weak acid and its conjugate base, or it contains appreciable amounts of both weak base and its conjugate acid. There are two different types of buffers. The first type of buffer is called an acidic buffer, which usually has a pH of less than 7. They are generally made from a weak acid and one of its salts. A common acidic buffer is a mix of ethanoic acid and sodium ethanoate, which has a pKa of about 4.75 when combined together. The pH can be changed by adjusting the ratio of acid to salt or by changing the acid. The second buffer is an alkaline buffer, which usually has a pH greater than 7. It is made from a weak base and one of its salt. A common alkaline buffer is a mix of ammonium and ammonium chloride solution. They have a pKa of about 9.25 when they are combined together. So how do buffers work? Well, buffers can neutralize small added quantities of either strong acid or strong base, which allows the average pH to be maintained. This makes either a weaker acid or base. Let's look at an example. Acetic acid is a buffer as it has a weak acid and its salt. It keeps the hydronium ion concentration the same by adding small amounts of strong acid or strong base. If a base like sodium hydroxide was added, it would react with the hydronium ions. So, more of the acetic acid would react with water, making the hydronium ion concentration return to its original value. If an acid like hydrochloric acid was added, then the hydronium ions from the hydrochloric acid would mix with the acetate ions to make acetic acid molecules. So again, the hydronium ion concentration has a very small increase and the pH barely changes. Now, if we look at this bottom equation, we have an acetic acid buffer. It reacts completely with a strong base and forms acetic acetate. It shifts the equilibrium to form a weak base. So, if you were to add a strong base to acetic acid, the acid and bases would mix together to neutralize to make acetate ions, a very weak base. And if you were to add a strong acid to a solution that contains a lot of acetic acid and acetate, it will react with acetate ions and shift the equilibrium to the left and form weak acid. Normally, a strong acid would change the pH a lot when reacted with acetate to generate acetic acid. However, converting a strong acid to weak acid is a buffer. The weak acid will come to equilibrium, and overall, it has a minor effect on the pH. With a buffer, the salts of weak acid and conjugate base resist changes of pH with strong acid and bases. It keeps the pH of the solution constant. Okay, now I would like you to try and identify which of these are a buffer. The first one is HCl and NaCl. And HCl is a strong acid, so this is not a conjugate pair, and you cannot make a buffer with a strong acid. This is not a buffer. The second one is HClO and LiClO2. HClO is a weak acid and LiClO2 is a salt, which breaks up into. This is not a conjugate pair as they do not differ by 1. This is not a buffer. Okay, third one, HF and KF. HF is a weak acid and KF breaks up into. Yes, this is a buffer. And last one, CH3NH2 and CH3NH3Cl. CH3NH2 is a weak base and CH3NH3Cl breaks up to. It is a salt. weak conjugate acid. Yes, this is a buffer. Now, remember to ask yourself, is everything weak? Must be weak acid or weak base. Nothing can be strong. And do we have a conjugate pair in solution? Really quickly, let's review the Henderson-Hasselbalch equation, which allows us to approximate the pH of a buffer solution. This equation can be used when appreciable amounts of conjugate acid and bases are in the solution. So, the ratio of conjugate base to acid has to be between 0.1 and 10. Second, it has to be appreciable amounts, which means enough of both. Buffers have high concentration of ions, so HA and A- have to be 100 times greater than K in solution. Buffer solutions are a very important chemical reagent used for many different applications, including chemical research, biological research, and in our industry. They are important because of the fact that they can resist changes in pH, which is key for many chemical reactions to be successful. Most chemical reactions are greatly affected by pH, meaning the rate of the reactions and the products produced can be altered by a change in pH. Buffers have many uses in our industry, including fermentation, dyeing products, cosmetic products, shampoos, and baby lotions. They are used in printing so that the pH of the paper and ink are controlled to make sure the ink appears and dries on the paper properly. Buffers are used to maintain a specific pH when producing leather to determine the texture of it. Buffers are also used in the solutions of calibration of pH meters. Okay, let's talk more specifically about cosmetic products. Buffers are used in the production of cosmetic and personal hygiene products to keep a natural or alkaline pH. Buffers prevent skin irritation as they stop the product from being too acidic or alkaline. If we look at shampoos, a buffer of citric acid or sodium citrate is used to achieve a slightly acidic pH. The buffer opposes the regular alkalinity of the products in the shampoo that could burn the scalp. Another example is soap, which has a high pH, so is buffered to have a pH of about 5.5. I'm sure you're all wondering about how baby wipes work, especially Pampers, so let's dive into the science behind them. Pampers Baby Wipe uses a mild cleansing lotion that is water-based to be able to clean the mess on the baby. Within the lotion is a citric acid-based buffer to help keep a low buffering pH system so that the natural pH of the skin remains the same. Baby's skin has a natural pH of 4.5 to 6. However, the mess inside dirty diapers can increase the pH, causing the skin to become easily irritated. So, Pampers uses buffers within the lotion to help keep the baby's skin at its natural and healthy pH. Another example of buffers can be seen in fermentation, meaning that buffers are used in the production of alcohol. In order to produce a high yield of fermentation, the pH must be maintained. Yeast is an organism. Therefore, if the pH is too high or too low, it could prevent it from growing or possibly kill it. The process of fermentation in beers is similar to when muscle cells are lacking oxygen. Muscles release carbon dioxide and lactic acid in fermentation. However, yeast releases carbon dioxide and ethanol. Yeast likes a pH between 4 to 6, so buffers are used to keep the pH within this range when baking or brewing. The buffer absorbs any extra acidity or alkalinity, thus the pH only changes if the buffer is neutralized. Now let's look at a practical example of buffers. You wish to prepare 19 liters of 1 mole sodium phosphate buffer with a pH 5.2. You have 1 mole monosodium phosphate and 1 mole disodium phosphate. How much do you need of each solution to make the desired buffer? pKa of 6.82 at 25 degrees. We insert the pH and pKa values into the Henderson-Hasselbalch equation. Subtract 6.82 from each side and take the antilog of each side of the equation. So, to make 19 liters of the desired buffer, combine 0.445 liters of disodium phosphate and 18.55 liters of monosodium phosphate. Combining these volumes will give us 1 mole sodium phosphate buffer with a pH of 5.2. Hence, we will need 18.955 liters. There are also buffers in our environment, which can be found in natural water, seawater, and soil. An environmental buffer is anything that helps to keep the natural environment balanced, hence protecting our natural ecosystem and preventing pollution. In natural water such as lakes and streams, the sediments within them are buffers that help support the aquatic life. Carbonic acid bicarbonate is a very important buffer in water surfaces. Limestone is a common form of calcium carbonate. Acid rain can assist the breaking of calcium carbonate, which produces bicarbonate. The water surfaces are always in equilibrium with carbon dioxide, creating a carbonic acid in water. Limestone and rocks in natural water react with the extra acid to maintain the desired pH of lakes and streams. The main buffers in seawater are bicarbonate and borates. These buffers help the ocean absorb the carbon dioxide that is released in the atmosphere. As the ocean absorbs more carbon dioxide, more carbonate and hydrogen ions are also created. This causes too many carbonate ions. So the ocean is buffered by creating more bicarbonate ions. If oceans become too acidic, the animals that build their skeleton and shells from calcium carbonate will no longer be able to. The pH of soil must be maintained at almost neutral for plant and microorganism to reuse nitrogen. The soil must absorb and release nutrients. Buffering capacity of the soil reflects how well the soil can withstand pH change. Different soils have different amounts of surface sites for hydrogen ions. When the soil has many hydrogen ions, it has a higher buffering capacities. Soils with clay and organic matter can withstand decrease in pH. Acidic buffered soils can withstand increase in pH. Neutralized soils can withstand increase in pH. Thanks for tuning in to Module 9. See you next time.